Welcome to This Explainer. Today, we're taking a journey right under the hood to demystify one of the most literally transformative inventions in human history, the internal combustion engine. We're going to break down this mechanical ballet of moving parts that somehow turns liquid fuel into raw driving power. It's a completely fascinating symphony of engineering, so let's get right into it.
Okay, let's dive right in. Have you ever actually stopped to wonder how controlled explosions end up powering your car? Because at its core, an engine is really just a machine designed to avoid manual labor by harnessing the violent, pushing power of fire. Instead of you pedaling or hand-cranking a mechanism, we're using literal explosions to do all the heavy lifting for us.
Section 1. Harnessing the explosion, from cannons to crankshafts.
So the fundamental problem early engineers faced was figuring out how to convert a chaotic explosion into reliable rotation. Imagine, just for a second, trying to use a cannon to turn a crank. You fire the cannon, the ball hits the crank handle, and it turns the shaft. Great, right? Well, except it pushes exactly once, and then your cannonball is gone. It's not exactly a sustainable cycle. To fix this, we replace the cannonball with a cylindrical piece of metal called a piston, and we trap it inside a metal cylinder attached to a crank shaft. Now, the explosion pushes the piston down to turn the shaft, but the piston stays trapped and then it's pushed back up by the momentum to repeat the whole cycle continuously.
So the crucial point here is understanding the absolute limits of this trapped piston's movement. We have top dead center, or TDC, which is the absolute highest point the piston can physically reach inside the cylinder, and bottom dead center, or BDC, which is its absolute lowest point. The total distance it travels in one direction between these two extreme limits is what we call a single stroke.
Section 2. The four-stroke cycle, the engine's heartbeat.
To make this piston do continuous work, we need a rhythm, the legendary four-stroke cycle. First up, intake. The piston pulls down, sucking in fresh air and fuel. Second, compression. The piston pushes up, violently squeezing that mixture together. Third, power. A spark ignites the compressed gas, absolutely slamming the piston down. This is the stroke that does the actual work. And finally, fourth, exhaust. The piston rises one last time, pushing all those burned gases out.
Now, you might be thinking these 4 steps happen in perfectly rigid, isolated little boxes. But they don't. It's actually incredibly fluid. The intake valves open slightly before the exhaust stroke is even finished. This overlapping helps pull fresh air in by using the momentum or inertia of the escaping exhaust gases. It's a clever scavenging effect. The exhaust valves also open right before the power stroke ends, just to ease the piston's upward push. And spark plugs? They actually fire just before the piston reaches top dead center. This gives the flame front time to propagate so the absolute maximum pressure hits exactly when the piston starts moving down again.
Okay, here is a foundational mathematical rule you absolutely have to remember about this whole setup. 1 complete cycle equals 4 strokes of the piston, which requires exactly 2 full revolutions of the crankshaft, meaning the engine has to physically spin twice just to get 1 single power stroke out of a single cylinder.
Section 3. Anatomy of an engine. Building the machine.
Let's move on and see how this physical architecture actually comes together. The foundation of it all is the engine block, containing those empty cylinders. Down at the bottom sits the crankshaft, spinning on microscopically thin layers of pressurized oil to prevent catastrophic metal-on-metal friction. Inside the block, the pistons, fitted with these expanding rings, seal in the explosive gases. And finally, capping the whole thing off is the cylinder head, which houses the precise valves and the spark plugs.
I'm sure you've heard someone brag about their 2.0-liter engine, right? Well, engine displacement is simply the total volume of air swept by all the pistons as they move from top dead center to bottom dead center. If you take the circular area of one cylinder, multiply it by the stroke length, and then multiply that by the total number of cylinders in the block, you get the displacement. It is essentially just a measure of the total volume of air the engine can breathe in during one cycle to generate power.
To get those cylinder head valves to open at the exact perfect millisecond, they're controlled by overhead camshafts, which are connected directly to the crankshaft by a timing belt or chain. Just look at the clever gear sizing ratio we have going on here. The gear on the crankshaft is exactly half the size of the gear on the camshaft. This means the crankshaft turns twice as fast as the camshaft, which makes total sense because remember our rule? It takes 2 crank revolutions for every 1 full cycle, and we only want the valves to open once per cycle.
But remember, we are literally containing thousands of violent explosions here. Without some seriously clever engineering, this machine would just completely shake itself apart from the sheer force. To tame that violence, engineers use crankshaft webs. These are elongated counterweights built right into the rotating shaft to balance out those heavy pumping pistons. Additionally, a massive heavy metal wheel called the flywheel is bolted straight to the end of the crankshaft. Its sheer weight and momentum drastically increase the rotational inertia of the entire system. It completely smooths out the jerky, pulsing power of those individual explosions into one seamless, continuous rotation.
Section 4. Engine Configurations Explained. Shaping the Power.
Now, what's really interesting is how form dictates function. Think about your everyday inline-4 engine. The cylinders just sit straight in a row. They're smoother, they're highly affordable, and way less complex. But the downside is they get far too long to fit under a standard hood if you start adding too many cylinders. On the flip side, we have V engines. By staggering the cylinders into a V shape, like a V6 or a V8, you create a much more compact block with a shorter crankshaft. This setup generates fantastic low RPM torque and saves a ton of space, though obviously it does require more moving parts and it is more expensive to manufacture.
Then you've got the flat Boxer engine, famously used in Porsches and Subarus. Here, the cylinders lay entirely flat and horizontally oppose each other. So when they fire, the pistons push outward at the exact same time. Honestly, just like two boxers throwing punches. This brilliant design effectively cancels out vibrational forces, giving you incredibly smooth power and a wonderfully low center of gravity. The trade-off? Well, it's incredibly wide, which makes it a total headache to access parts like spark plugs when they're nestled right up against the edge of the engine bay.
Section 5. History and Fuel Types. The Evolution of Combustion.
Let's take a quick step back and look at the history, because it was just this rapid, brilliant burst of innovation. Back in 1860, Etienne Lenoir created a double-acting engine running on illuminating gas, but it only squeezed out about 4% efficiency. The massive breakthrough came in 1876, when Nicholas Otto realized that if you compress the fuel mixture before igniting it, your efficiency absolutely skyrockets to around 30%. Soon after, in 1882, James Atkinson tweaked the mechanical linkage to prioritize thermal efficiency over raw power, a brilliant concept we actually still use to get great fuel economy in modern hybrids today. And then, in 1893, Rudolf Diesel pushed compression to the absolute extreme, creating a heavy-duty marvel that didn't even need a spark plug.
And that brings us to the fundamental difference between gasoline and diesel engines. Gasoline engines use a spark plug to carefully, precisely time the explosion. They require fuel with a high octane rating, which basically just means the fuel actively resists exploding too early, because that's a very dangerous, engine-destroying condition called pre-ignition. Diesel engines, on the other hand, throw out the spark plugs entirely. They squeeze the air so incredibly tightly during the compression stroke that the raw, brutal heat generated is literally enough to spontaneously ignite the heavy diesel fuel the precise moment it gets injected into the cylinder.
50. I really want you to just let that number sink in for a second. If you are driving a standard 4-cylinder car and your engine is cruising at a very modest 1500 RPM, 50 distinct, perfectly timed, intensely violent controlled explosions are happening inside your engine block every single second. 50 times a second. It is an absolute masterpiece of mechanical synchronization.
We completely take it for granted, don't we? Just turning the key and driving down to the grocery store. But under that hood is a heavy metal block that is literally taming millions of fiery explosions, continuously and reliably, just to propel you forward. It's harnessing fire in a truly Promethean way.
And this brilliantly illustrates the core magic of the whole thing, captured perfectly by engineer Bartosz Janowski. Classic engines really do have something almost mythical about them. They aren't just inanimate hunks of metal. They are intricate, dancing mechanisms perfectly synchronized to create carefully controlled conditions for harnessing raw fire.
So, the next time you turn your key or press that ignition button, take a split second to think about what's actually happening. Will you picture the mechanical ballet, the perfectly timed valves, and the rapid-fire explosions powering your journey? I really hope this explainer gave you a newfound appreciation for the incredible engineering sitting right under your hood. Thanks so much for exploring the internal combustion engine with me, and keep that curiosity fired up.